And with that short break, we come to the last speaker of today's session, last invited speaker. This is Max Marian, and I'm very happy to introduce Max here. Max studied at the Friedrich Alexander University of Erlangen-Nuremberg, where he also obtained his PhD degree, working on numerical design of surface structures in lubricated tribological contexts. Then he stayed on a bit and is now professor in the Universidad Pontificia Católica de Chile. And with that, he will talk to us about predicting EHL thickness parameters by machine learning approaches, which is a topic that I find very, very interesting. And with that, Max, please.
Yeah, thank you, Norbert, for introducing me. I hope you can see my screen and hear me well. So yeah, thanks for the introduction. Hello, everyone, and thanks all for switching on into this webinar and my talk, and also special thanks to Martina, Michael, and Norbert for inviting me to speak today about elastohydrodynamic contacts and how we might predict their behavior by machine learning approaches. Yeah, but before we get into any details, let's start with the big picture. And why we would want to predict the behavior of mentioned contact types. According to Holmberg and Eremir, around 23% of the world's energy consumption originates from tribological contacts, and of about 20% of that is used to overcome friction, and 3% is used to remanufacture or replace worn parts due to wear and wear-related failures. So to get a better idea of what these 23% mean, let me express it in an energetic way. This corresponds to annual losses of 119 exajoule per year. And exa, that's the one with 19 zeros. I don't know about you, but I'm always having a hard time imagining what that actually means. But maybe this one might help out. So 1 exajoule corresponds to the energy of an asteroid and the size of the Egyptian Cheops pyramid hitting Earth with 20 kilometers per second. So we are losing this kind of energy 190 times a year, only due to friction and wear in tribal contacts. Now, for me, this sounds quite a lot, doesn't it? However, by really understanding tribotechnical systems and developing new concepts, new materials, new lubricants or surface technologies, we might substantially reduce friction and wear in various applications and vehicle and machinery and any other equipment. So, as stated, this covers manifold applications such as brakes or brake pads, clutches, the piston cylinder liner contact, thrust and internal bearings, so gears, the cam follower, roller and ball bearings, or also load bearing implants. And within all these applications, we basically can break down the essential contact types or contact pairings or the geometries into parallel and conformal contacts on the one hand side, and on the other hand side on concentrated contacts, which we can distinguish in line contacts and point or elliptical contacts. The use of lubricant, of course, is an effective way, both in nature and in technology or industrial technology, to reduce friction and wear in highly stressed tribal contacts due to the partial separation or the complete separation of the contacting partners by an intermediate medium, the lubricant, which generally has a lower shear resistance. And deforming of a separating hydrodynamic fluid film depends on the gap geometry, the relative movement of the contacting surfaces, the viscosity of the lubricant, and also the adhesion conditions. And if lubricant is drawn into the contact, as exemplarily shown here for an radial hydrodynamic journal bearing, hydrodynamic pressure can build up, and it can thus lift the surfaces and separate the surfaces, and thus with sufficiently high velocity and or viscosity or lower loads, the lubricant or the fluid regime can be transitioned from boundary to mixed and finally fluid or full film separation, which means first we have a partial separation of the contacting bodies, and with higher velocity or viscosity or lower load, we might have a full separation of the contacting bodies. And the coefficient of friction typically follows the well-known Strybeck curve that probably all of us are very familiar with. In the case of more heavily loaded contacts, where pressures can reach up to 4 gigapascal, which roughly corresponds to the load of 7 African elephants standing on the area of a human finger thumbnail, as we have, for example, in rolling bearings, there's some elastic deformation of the contacting partners that adheres to concentrated contact geometry, and this can generally be described by the Hertzen theory and the Hertzen pressure. Due to a lubricant, there's also a superimposed formation of hydrodynamic pressure. And in the area of contact inlet, compared to the Hertzen pressure distribution, we generally get an earlier pressure increase, which occurs to the lubricant compression. And in the central part of the contacting bodies, we have almost parallel film height. And there's an additional constriction in the outlet region of the contact, which is also accompanied by an additional hydrodynamic pressure peak. Typically, the elastic or the lubricant film thickness and the elastic deformation are of a similar order of magnitude for elastohydrodynamically or EHL contacts. And the elastic deformation and the fluid film formation also depend on the stress collective and acting on the contact. Basically, the resulting pressure and the fluid film distribution is determined by the geometries of the contacting bodies with radius r, for which we can calculate an equivalent radius, and the mechanical or the material behavior of the contacting bodies, namely the elastic modulus E and the Poisson's ratio nu, for which we can calculate an equivalent elastic modulus. Further, the kinematics influence the contact behavior, namely the velocities of the contacting partners, the velocities U, for which we can calculate some characteristic properties like the hydrodynamically effective velocity UM and the slide to roll ratio SRR. And finally, of course, as relevant lubricant properties, we have the density rho and the viscosity eta of the fluid that determine the contact behavior. Depending on the operating conditions and the involved materials and the lubricant, different effects can dominate the contact behavior, especially elastic effects and or the piezo viscosity of the lubricant, which is the increase in viscosity under pressure. And using these kind of dimensional parameters that were suggested by Johnson, we can differentiate between an isoviscous rigid, an isoviscous elastic, piezoviscous rigid, and a piezoviscous elastic regime, as well as this kind of transition regime in between. So what I want to present in the following within this presentation, I would like to briefly introduce the conventional ways to numerically model such EHL contacts, and I will introduce two analytically solvable proximity equations. And then the main part or the core part will then focus on our attempt to use machine learning approaches to predict EHL film thickness, which was done in a close international cooperation with the University of Erlangen in Germany, the Universidad de Sao Paulo, and the Universidad de Chile. And finally, I will briefly summarize my talk with our short key findings. So let's start with the simulation of EHL contacts. Generally, this involves various physical domains ranging from, of course, the lubricant hydrodynamics, as we have seen, contact mechanics, i.e. the elastic deformation. Potentially, there's thermodynamics and fluid hydrology involved. If we would neglect non-Newtonian and thermal effects, as well as mixed lubrication, which I won't put any focus within this presentation, we require both solution of the hydrodynamics and the elastic deformation. And if flow and structural mechanics interact with each other, this is generally referred to as fluid structure interaction. And since both solutions influence each other, we need a suitable coupling for the both domains. One way of coupling would be to perform a solution of the hydrodynamics, followed by a solution of the deformation due to the given pressure. And this is called weak coupling. If the step is only performed once, we speak of unidirectional coupling, and it's the most simple approach, and the interaction between the fluid and the structure is not sufficiently considered. Generally, in a weak coupling, therefore, the steps are usually repeated sequentially. So there's a bidirectional weak coupling until a defined convergence criterion is reached. In the strong coupling, on the other hand, we solve the two discretized differential equations in one joint algebraic systems of equations. Generally, it is possible to use the full Navier-Stokes equations to solve EHL contact problems. In this case, however, the lubricant has to be meshed in the gap height direction also, which makes normalization and mesh transformation quite difficult, and usually we have quite some instabilities there due to an over response of the elastic deformation to the surface pressure of the previous iteration step. Therefore, the hydrodynamics is most frequently represented in the form of the Reynolds differential equation. In the past, both weak and strong coupling have been used by various scientists all around the globe to solve EHL contact problems. The former, the weak coupling in the form of sequential solution, it represents both the first implemented and today still the most widely used coupling. And the first implemented or the first works that have been implemented use the so-called inverse iterative method. Here, the Reynolds equation is solved for the lubricant gap at a given pressure, and typically half space approaches are employed to compute the elastic deformation. Secondly, there are direct iterative methods which solve the Reynolds equations for the pressure, and the multi-grid or short MG method accelerated these kind of algorithms, and also suitable and also the introduction of the multi-level multi-integration or short MLMI method, as well as some relaxation procedures allowed to calculate these kind of contacts at higher pressures. And with these approaches, we also have to mention the names of Werner and Lüprecht, who've been some pioneering work in the semi-system approaches. The weak coupling, on the other hand, or these weakly coupled solutions are contrasted by those of the so-called strong coupling, where we simultaneously solve the equations. But if we use the elastic half space models to calculate the elastic deformation, we result or we get to a fully filled matrix in a nonlinear system of equations, and all mesh points basically are related to each other by integral equations, which then involves a lot of memory and computational effort. In the past, for example, already for simple point contacts, this has led to the fact that calculation was limited solely by the computer hardware, and this was one of the main reasons why in the past the weakly coupled solutions have dominated. But in order to obtain a sparse matrix and lower computational memory requirements, Hapchi and co-workers proposed to replace basically the elastic deformation calculation by a finite element formulation, and also to discretize the Reynolds equation by a finite element approach. And due to the strong coupling, there's a very good convergence behavior of the solutions, which means a rather small number of iterations required to find the solutions. And further, one of the main benefits is also that it allows the use of commercial software algorithms already out there, like finite element software, that we just have to implement basically our equations and teach the software how to solve it with well-known and well-established algorithms. So still, EHL equations are quite complex and computationally expensive, and in many cases sufficiently accurate and like a computationally much more efficient incorporation of EHL effects into higher level multi-body simulations or system simulations. Analytically solvable proximity equations are generally used to estimate integral fluid film parameters. So to generalize EHL contacts and the results, there were non-dimensional similarity groups introduced. Though we have to mention the names Dawson and Higginson, who defined a group of velocity, material, and load parameters, as well as a film thickness parameter. And they basically proposed curve-fitting regression equations. From now on, I will refer to them as proximity equations that relate those parameters based upon numerical simulation results. And later, Block and Mohs proved that these 4 parameters could be transferred into 3 independent parameters, thus introducing a load and a viscosity parameters in addition to the film thickness parameter. To estimate, for example, the minimum film thickness in an EHL infinite 2D line contact, Dawson and Higginson proposed an analytically solvable regression equation as a function of the material, the velocity, and the load parameters. And based upon more advanced isothermal EHL simulations, these parameters have been modified and extended by various authors to also cover 3D point contacts and also allowed the determination of the central film thickness. Basically, due to the transformability of the aforementioned non-dimensional groups, you can also use the parameters from the block and from suggested by Block and Mohs to calculate the EHL film thickness parameters. So basically, these are polynomial regression equations to estimate, for example, the minimum film thickness, independency of the load parameter, and the viscosity parameter. So in this case, generally the minimum film thickness increases with a decreasing m and with an increasing L. And this would be some kind of curves for the central film thickness, which is less influenced for a wide range of the m parameters. Generally, there have been several variants developed and published over the years, mostly to cover, for example, a wider range. When we compare, for example, the equations that have been suggested by Nijenbening in comparison to Amrag and Dawson, which have been traded in this or determined for data in this kind of or in this range. And mostly, they have been developed to cover wider ranges than the initial equations, and also to be valid, for example, in the more isoviscous and or the rigid regimes. And to describe non-dimensional groups and parameters or the film thickness equations, basically they can deliver quite reasonable agreement with many lubricants that was experimentally verified by the British authors, for example, by interferometric film thickness measurements. However, there could be some deviations under certain conditions due to fluid compressibility, thermal effects, or shear thinning, starvation, or also surface roughness. And all these aspects are not or have not been fully considered in the original numerical solutions based upon which these kind of proximity equations were derived. But these effects can also be taken into account if we employ some kind of correction factors, Cx, which are simply multiplied with the film height parameters to obtain a corrected fluid film thickness. In the original numerical solution, the density pressure relationship was modeled according to Dawson and Higginson, but the density was not considered as an input variable for the non-dimensional groups, and also not for the film thickness equations. We know that the lubricant compressibility plays no major role in the minimum film thickness formation, but the central film thickness formation can be influenced under certain conditions, and therefore we can adjust the predictions for compressible fluids from the incompressible approximations with the base density rho 0 using this kind of correction factor, whereby any model could be used to calculate a density at the respective friction pressure pH. The deduction of non-dimensional parameters in the film thickness equations was also both based on isothermal considerations. However, if we have high speeds and high velocity differences or high slip of the wrapping surfaces, there might be some local temperature that exceeds the mass temperature of the contacting bodies and also influence basically the viscosity of the lubricant, and thus also the film thickness. So for example, Murch and Wilson, they introduced the so-called thermal stress parameter Q, which also includes the viscosity temperature coefficient, and to determine the thermal film thickness reduction, basically, which was later extended to also cover the slight to roll ratio as RR. So here, basically, we can see the thermal correction factor versus the thermal stress parameter and dependency of the slight to roll ratio. Similar to thermal effects, Newtonian fluid behavior or shear thinning of the lubricant at high speeds and at high slip. This can also affect the minimum film thickness and change also the profile in the contact center. Therefore, a number of authors came up with different correction factors. This, for example, an equation suggested by Baer, which also contains basically the slight to roll ratio, the Carreau exponent n, and the Weissenberg number. So basically, there are also some correction factors available. Also, in the original determination or derivation of the film thickness equations, some fully flooded conditions were assumed. Sort of basically the pressure or the elastohydrodynamic pressure buildup can happen in any distance from the contact center. However, there are cases where contacts may suffer from starvation because there's high speeds, highly viscous lubricants, or simply there is not enough lubricant supply. And then basically the starting point of a hydrodynamic pressure generation is closer to the contact center, and the generated or the transportable lubricant film thickness basically smaller compared to the one for fully flooded conditions. And basically fully flooded conditions are reached when the distance between the contact inlet where we allow pressure buildup and the contact center, when it ceases to affect the film thickness. And Dawson and Higginson basically suggested taking the fully flooded staffed boundary M star and the inlet location of the contact into account to calculate some correction factors to also cover starvation effects. Yeah, and finally, it is well accepted that the surface topography in terms of any kind of stochastic deviations from the smooth surface due to manufacturing, or also intentionally produced surface features, or such as surface textures or structures, that they have a decisive impact on the film formation in EHL contacts. And basically, with decreasing lubricant film thickness, the effect or the impact of the surface roughness is getting stronger on the pressure buildup and also on the film thickness development. And when we approach very low film thicknesses, there might also happen some kind of solid asperity contact, which we refer to as mixed lubrication, where basically the load is shared by an hydrodynamic pressure buildup and the solid asperity contact. And a first approach to also consider this influence of the surface topography was introduced by Chu and Cheng, based upon some statistical consideration of surface asperities in terms of microhydrodynamics and load sharing. And similar to the very well-known flow factor method from Patti and Cheng, they derived corresponding correction factors to adjust the minimum and the central film thickness depending on the orientation of the surface topography and also the ratio of the smooth lubricant gap to the quadratic mean surface roughness, so what we know as fluid film parameter. And to quantify the spatial orientation of the surface topography. They employed the so-called Picklinic factor, which basically is a ratio of the characteristic correlation length of two mutually orthogonal measurement devices. So basically, this is a bunch of correction factors that can further adjust the predictions from the proximity equations. This is an overview of all the equations that exist for the minimum film thickness, the central film thickness in infinite 2D line contacts, as well as point contacts, or 3D elliptical contacts, that have been published over the years. And we can also see that there's quite some approaches for actually correcting these equations by factors addressing fluid compressibility, thermal effects, non-Newtonian behavior, starvation, or surface roughness. So what I've previously shown was just only a very brief excerpt from all the work that has been done in that direction. We always have to bear in mind that all the film thickness equations and also the correction factors were originally derived from different numerical data, and therefore they have different ranges or individual ranges of validity. And while a comparison with experimental data is difficult for infinite 2D line contacts, this possibility exists for point contacts and using experimental studies using interferometric film thickness measurement. And basically quite some good agreement has been reported, especially for the central film thickness, even when using lubricants with shear thinning characteristics and when you expect thermal effects, etc. And there's also quite a good agreement when we use these equations for the central film thickness outside of the stated ranges. But it's extremely important for the minimum film thickness that we only applied inside the stated ranges, in which basically was the base for building these kind of equations, because outside of these domains, the equations are greatly influenced and could not predict all equations very well. So 2 years ago, we published a review article, open access, where you can find much more detail and information on all these aspects. And in that review article, basically the research, or doing the research for that review article, gave us the idea that we already hypothesized that machine learning approaches could provide an opportunity to predict the relevant EHL film thickness parameters more accurately and effectively, for example, in terms of speed and or also the flexibility of what we can predict. So, yeah, we have already heard quite a bit about machine learning within this webinar series. Basically, machine learning, shortly ML, and artificial intelligence, they're rising stars in many scientific disciplines and industries, and high hopes are being pinned upon them. And essentially, ML is part of AI and thus originally a subdomain of computer science. And AI and ML are formed by logic, probability theory, algorithms theory, and computer science. In the first step, ML involves designing computing systems for any kind of special task that can learn from training data over time and develop and refine experience-based models that predict any kind of outcomes. Thus, the system can be used to answer questions in any given field. And there are a number of different algorithms that can be used for ML, whereby the suitability of each of the algorithm approaches is strongly task dependent. Generally, we can classify these kind of machine learning algorithms into supervised, unsupervised, and reinforcement learning. For supervised learning, the algorithm basically learns a relation from any given data set or set of input and output. And during the learning, a teacher or an expert basically provides the correct input and output. And in unsupervised learning, the algorithm generates a statistical model that describes a given data set without the model being evaluated by a teacher. Basically, while the classification into these three learning types, supervised, unsupervised, and reinforcement learning, is well accepted in the scientific community, there's still no consensus which kind of algorithm should be assigned or can be assigned to which category. So what I show on this slide is only one possible allocation, but literature will display you different kind of classifications. But anyways, the intended usages of these numerical algorithms they're manifold, and there is a very broad variety of available approaches, ranging from artificial neural networks, ANNs, to, for example, decision trees, support vector machines, or also rule-based learners. So basically, there's a whole variety of approaches that we can employ. And as already heard within the other talks within this very nicely organized webinar series, there are quite some machine learning approaches that also found a way into tribology, where they can help us in sorting through a complexity of patterns and also identifying trends within the multiple interacting features and the processes involved in tribological systems. As can nicely be seen in a recently published article collection and in a respective review article that we wrote on current trends and applications of machine learning in tribology, published in the journal Lubricants. There's an increasing number of published research that aims, for example, at monitoring and controlling and analyzing, designing, optimizing, or predicting driver systems in various fields of application. This can range from lubricant formulation to drive technology, to design of composite materials, to manufacturing or surface engineering. And it does not only cover like single scale phenomena, but we can find works on the nanoscale, on the macro scale, as well as micro scale. And the ML approaches so far have employed different kind of databases based upon experimental data, which is the vast majority of the works that has been done so far, which fits very nice to discussion we had during the first presentation from Georg Vorlaufer. But there's also some amount of studies that have employed numerical databases or even literature databases. Yeah, I won't go into any more details of all the exciting stuff that can be done. We have seen some very nice examples within this webinar series. But I would like to use this opportunity for some shameless promotion of a second edition of this special issue, which we entitled Recent Advances in Machine Learning and Tribology, which was just open for submission until mid of the upcoming year, and we would be more than happy to receive some submissions from you. So let's come back to the topic. Basically, our general idea of what I want to present the following was to train machine learning approaches to predict lubricant film parameters in EHL contexts as a function of standard input variables, as is also accomplished by the well-known proximity equations. And in this context, the work was based on the hypothesis that ML approaches can predict relevant EHL film parameters, such as, for example, the central film thickness or the minimum lubricant gap in 2D line and 3 circular point contacts more efficiently than sophisticated simulation models, and with higher accuracy and flexibility than the well-known proximity equations based upon the non-dimensional groups. Thereby, we addressed the following research equations. How accurate are the predictions of ML? In our case, support vector machines, Gaussian process regression, and artificial neural networks. As we can, for example, see the latter one exemplary on the left-hand side of the slide, compared to the proximity equations. The second research question: what is the influence of the training data if we use, for example, the non-dimensional groups instead of the original input to train the ML approaches? The third question we wanted to answer was how do the artificial neural network architecture and the structure affect the prediction quality? The fourth question what is the influence of the size of the data training database? And the fifth one, is it possible to determine locally resolved film thickness distribution, like the film thickness as a function of the contact length instead only of 2 integral parameters? So our overall approach is illustrated on this slide. At first, we define the data we need, including the original inputs, the non-dimensional parameters, and subsequently we constructed a design of experiments based upon an Latin hypercube sampling, and calculated all the trial points that we sampled by a finite element method-based EHL model, and also used proximity equations to predict the integral film parameters. Afterwards, we split the data into a training data set and used this training data to build a support vector machine, Gaussian process regression, and artificial neural network ML models. And we also split the data into test data to evaluate the prediction accuracy of our models. And for that, we use the coefficient of determination R². This slide shows the parameters that we write within the given boundary conditions for the 2D line contact and the 3D point contact. They were sampled using a Latin hypercube sampling and with 1,500 and 1,000 datasets respectively. And moreover, we investigated for a 2D case to what extent a reduced database with only 600, 300, and finally only 100 data points, how this affects the prediction quality. And we trained all the models first with the original input parameters that we also put into EHL simulation. And also we trained it with the non-dimensional parameters, G, U, and W, as well as the most parameters, M and L, and had a look what this does to our prediction accuracy. The database was created using an EHL simulation model based upon the finite element method, full system approach that was suggested by Hapchi and co-workers. So on the left-hand side, we can see the solver flowchart. And the right-hand side, we can see the solution domains. This is for the 2D line contact, and this is for the 3D point contact, making use of the plane symmetry. At first, the model is initialized using Hertzsprung values, and the elastic deformation is calculated for an equivalent body. Subsequently, the EHL problem is computed fully coupled, whereas the Reynolds equation is solved in a weak form on the boundary of the elastic body. And the whole model was implemented constant multiphysics, which is kind of state of the art now, so there's nothing really special about it. The results of the HTML simulation might look, for example, like this. Here we see exemplary lubricant gap and pressure distribution for different, basically most parameters for different load and viscosity parameters. Whereas basically we can see that the hydrodynamic and or the elastic effects are more or less dominant depending on the parameters or the operating conditions. Further, we employed various ML regression methods, including support vector machine, Gaussian process regression, and artificial neural networks. All the data, the in and output, were normalized to values between -1 and 1. And the models were developed using training data to provide basically the best possible prediction for unknown test data. For this purpose, we split the data set into 85% of training data and 15% for testing. So in detail, we had a linear epsilon insensitive support vector machine. Basically, the support vector machine, it represents an object set by a vector within a vector space, and hyperplanes within these vector space are used to separate the data points, and kernel functions are used to transform the vector space into a higher order dimensional space, so we can basically separate the interlaced vector groups linearly. Moreover, we had a Gaussian process regression, non-parametric probabilistic model that was which explains basically the response by latent variables from a Gaussian process and explicit base functions. And finally, we had a multi-hidden layer feed-forward backpropagation ANN, which was trained by the Levenberg-Marquardt algorithm. So basically, ANNs are inspired by natural brains and an architecture that involve a number of simple but very highly interconnected information processing elements, the so-called neurons. And transfer or propagation functions determine the neurons network input based upon output weighting, whereas the calculation of the output is achieved by activation functions considering some kind of threshold value. And during the training of the ANM, the weightings and the thresholds are adjusted to optimize basically the overall prediction quality. And the topology of or the architecture of an ANN, like how many neurons are parallelly arranged in each layer, how many hidden layers there are in between the input and the output, etc. This needs to be tailored to the respective application of what we want to predict actually. Okay, so finally, let's check out some results. We start with the prediction from the support vector machine and the Gaussian process regression. There's a lot of going on the slide, but I will try to guide you through. So basically in the table, we can see the R square values against, this is always against the testing data. And in the graphs on the bottom, we can see the predicted value versus the calculated value. So basically, the closer R square gets to 1 and the less deviation from this 45-degree line we have, the better is the prediction accuracy by both the approaches. And we can see that values calculated with the EHL simulation and the ones we predicted with the SVM and the GPR, that they quite correlated quite well, and that we reached coefficients of determinations of up to 0.99. So these coefficients of determination were partly higher than the R square values that we obtained when we employ the analytically solvable proximity equation. And when we compare both the SVM and the GPR proved to be slightly superior to the SVM. So when using non-dimensional groups like the UGW or the ML parameters, instead of the original input data for training purpose, the values were predicted with a substantially lower accuracy or even like totally insufficiently. The R square values that we had there fell well below 0.9 and almost to 0 for some cases actually. Like here, for example, we are approaching 0. And this like inferior prediction accuracy in our belief can be traced back to redundant input variables for the different output variables, because with the similar, we can have similar dimensional parameters that can result from different original input data, and with similar dimensional parameters we can result or finally obtain different predicted film thickness or for example, different minimum or central film thickness. And we believe that these inconsistencies in the database led to problems in the training of the SVM and the GPR. On this slide, we can see some results for the neural networks, namely the coefficient of determination for the prediction of, again, the central and the minimum film thickness for the 2D line contact, and also for we have it for the 3D point contact. Again, the R square values are against testing data, and here we write the number of neurons per hidden layer, as well as the number of hidden layers. So the number of neurons per hidden layer where we write between 20 and 20, and the number of hidden layers between 1 and 3. Therefore, we again use the original input values, and we can see that the EHL film parameters were predicted with high accuracy, and we reached R square values above 0.99 by some of the ANN configurations. We can see that the number of the neurons within the in each of the hidden layer, it played a less dominant role, but the number of hidden layers that had a more decisive impact on the prediction quality. And therefore, the lowest R square values resulted in only one hidden layer, followed by 3 and finally 2 hidden layers with the highest accuracy. And regarding the number of neurons, the configurations with more than 10 neurons proved to be quite good. So since 12 neurons in 2 hidden layers gave us the best results, we kept this configuration for the following predictions. Here we can see also the predicted with calculated values for this kind of configuration. The 3D point contact featured slightly higher R-square values or better prediction accuracy against the testing data compared to the 2D line contact, which may be due to the considerably larger database for the latter, and some overfitting basically for the 2D case. Similar to SVM and GPR, training the data with only the dimensional groups instead of the original input parameters resulted in a downgraded prediction accuracy due to the inconsistency in the training database. We further varied the activation functions of the neural networks. This is still for the ANN with 12 neurons in 2 hidden layers after training with hyperbolic tangent, as in the cases before, as well as a sigmoid logistic and a linear identity activation functions. Please note that the output and propagation function were kept constant, and only the activation function was varied. And here we can see that the sigmoid and the hyperbolic tangent function both led to R-square values above or beyond 0.99, while the linear identity resulted in slightly downgraded prediction quality. And to minimize the efforts required to train or generate the database, generally it's advisable to keep the training data set as small as possible without affecting the prediction accuracy. So basically, we can see here the R-square values for the infinite 2D line contact with a varying number of input training data, and even when the original training data was reduced to 600 training data points, less than half the R-square values were at high level above 0.99, thus showing slightly R-square values, better R-square values than the 1,200 training data sets, which might imply some overfitting. And we can see that slowly for 300 and 100 data sets, the R-square values decreased. And the deterioration of the prediction quality can also be seen here in the graphs of the predicted versus the calculated value. Here we have the training data set with us. We're training with 600 training data sets with the training with 100 data sets. One last aspect I would like to show you is the prediction of the local lubricant film distribution. This is for an infinite 2D line contact. Basically, we use the local film thickness, in other words, the film thickness as well as the contact length parameter X as a training data. And thereby we reached R-square values of 1 against the testing data, including all the data sets and positions along the contact length that we obtained. We can also see from this graph the quite nice prediction accuracy of the FEM-based EHL simulation model and the ANN prediction, and only in the range of the contact outlet, basically we got some kind of small overshooting here directly in front of the local constriction of the film cap. To compare the execution time of the FEM-based simulation and the ANN for solving the film thickness equations, basically we compared it for a data set that was not included in the training data, and we calculated with both methods on the same computer with the same discretization, and thereby the ANN was basically 50 times faster than the FEM model, while the calculation time is probably comparable to what we have when we solve proximity equations. And therefore we believe by incorporating the ANN into multi-body dynamic simulations or system simulations, we can improve the accuracy in friction and dynamics analysis or identification of critical operating conditions without negatively affecting basically the computational time. So this brings me almost to the end of my talk. I'll just wrap things up really quickly. Basically, I've shown you that ML approaches could predict film thickness parameters more efficiently than sophisticated EHL simulations. And we could verify that the ML outperforms analytically proximity equations based upon non-dimensional groups. Secondly, in contrast to proximity equation, it's important to use the original input parameters instead of the non-dimensional groups. Third, the architecture of ANNs, and especially the number of hidden layers, influences the accuracy. And for the data set of this contribution, we found that ANNs with 12 neurons and 2 hidden layers were quite favorable. The fourth point was the size of the training data set that is required within our study for training using 12 input parameters, we estimated that roughly 600 training data proved to be sufficient to reach high R-square values without overfitting. And the last point, in addition to global parameters, it's also possible to predict the local fluid film thickness distribution, which might also be quite interesting to integrate this in multi-body and system simulations. So we hypothesize that in the future, this might bring really added value for higher level simulations and to actual engineering system design processes. That's all from my side. Again, thank you very much for having me in this webinar, Norbert, Michael, and Martina. And thanks for every single one of you in the audience for joining. I appreciate it. And yeah, I'll be happy to answer your questions.
Yes, thank you very, very much for that very, very interesting talk. And, yeah. Also a short welcome to Martina, who has joined us now. And then, yeah, the question is, are there questions in the chat?
There are none so far.
Okay. Anyone in the Zoom conference have a question?
Well, I might have a small curiosity. Sorry I joined late. Thank you very much for giving the talk, and hello to everyone who are still here. Well, it's very impressive work, very nice talk. I was curious about the last part. Actually, I was curious about the infrastructure in the last part that you were mentioning, where you were comparing computational time for this kind of workflow. So I'm wondering, this computational time is based on a single machine that you use, for which you can do the whole thing and you can store the whole thing. How is it set? How is the setup for a standard?
Yeah, basically, well, basically the calculation or the simulation is computationally not overly expensive. So basically, you can run this on like simple workstations. And what we do is because for training the artificial neural network, we exported all the data that we had in the FEM model. Basically, we had the lubricant gap, but also as a function of the contact length parameter, like locally resolved. And basically, we only took every 10th parameter to train the ANN model. But when we query, basically everything from the ANN models has been implemented in MATLAB using the machine learning interface. And basically, there we can query any kind of position of the lubricant gap and predict the behavior. So what we did is we queried the same discretization from the neural network as we had from the FEM to have a fair comparison, so that we basically in the end end up with the same amount of data points that we predict. And basically we just ran both approaches on the same computer after each other without any other process, and track the computational time. The interesting part, we had like also these 19 seconds, that does not sound very much, because it's a very simple case of an infinite 2D line contact. So basically we have only basically only one dimension in contact or in fluid flow direction. It sounds not very much, but we're approaching a couple of minutes, maybe 7 minutes, if we already calculate a 3D point contact. While we don't expect any further increase in the already pre-trained ANN prediction. So here we have to differentiate in between the training of the ANN, which is also not very long, but in a couple, like in the order of a couple of minutes, and on the other hand, like only querying the ANN for a result that, like the ANN that was previously trained, and then we're getting pretty fast, and that makes it attractive to actually replace the proximity equations that have been around for quite some years.
Cool, thank you.
That did answer the question.
Yeah. Thanks.
Yeah, I actually have a question into a similar direction, which, I mean, first of all, so we are using either the proximity equations, as you call it, or we are solving like Hapchi, or you are doing the finite element problem, or we are using multi-grid code to run the simulation and then get our contact solution. So if, I mean, just from a practical point of view, like if I look at the proximity equations, they can be written into a paper and I can publish them. If I come with my neural network, how would this be made available to everyone? And can I don't have any experience in the neural network world. I mean, is it just like, can I just save the trained brain somewhere and then use it? So I mean, like you do the training and I just use it, or as end user somewhere?
Basically yes. So basically we would be able to provide any kind of pre-trained ANN that you can simply run. So that is possible. Actually, we're currently working with the Tribonet platform to provide it online. We just have to add some more explanations, and also because we had the comments in German, and we're converting it now into English, and then we want to make it publicly available. Yeah, in that sense, we also have to, or I also have to mention maybe that surely, like the MATLAB toolboxes, they're quite nice to because they're quite easygoing and you can get started pretty quickly. But surely maybe it might not be the most efficient language, and might also not fit to incorporate the model into any other kind of software. So basically, it would also be possible to use, for example, the data set that we created to train other models, for example, Python or whatever, which could then be maybe better incorporated into any software in mind. So basically, that's all also there. But the training of the ANN itself, it's not the very critical part. Because it's also very quickly done. So we're talking about a couple of minutes to train the ANN with the input data, and then we just vary the basically the configuration or the architecture. The tricky part is the generation of the database, because you want to have a lot of converged data points in your database. You want to somehow maximize the validity range without changing anything in the model, because on the one hand, for example, if you're in a very low load, or in the let's say the very rigid isoviscous regime, you have other effects dominating. You might, for example, play around with the stabilization of your numerical model, maybe the discretization, to have conversion solutions there, which might influence on the other end maybe the results. So basically, the challenge for us at the beginning was, which took probably 70% of the time of this project, to find a setup for the FEM model that allows us to generate the database in a wide area without changing any configuration of the FEM model. So that was also the kind of the challenge.
Yeah, that's good. I have two more very short. I mean, the one is maybe not that short, but the first one is, as someone who has been studying fluid rheology, so that's always challenging. Of course, you are kind of tied up in your approach, quite tied to this finite element model, right? And I mean, we all know that there's this never-ending fight between, be it Beer-Weiner, Spikes, Imperial College, somebody saying Newtonian is good enough, the next one saying I use Eyring or Caro or whatever equation. So yeah, I guess there's still quite a bit of uncertainty coming there. But my real question is actually, so when you showed the regression parameter of the neural network for for all the input parameters, and then compared that to the dimensionless number groups, I was quite surprised that you said they don't fit that well. And do you think that actually, I mean, we have been using the non-dimensional groups because we always thought they kind of, they signify similarity in a way that we have deduced the number groups from a physical interaction of parameters, so that's why they give us the similarity.
Yeah.
But do you think we can use this method also to actually study such assumptions and think about whether
Yes.
maybe our non-dimensionalist group are not physically based or not fully physically
Yeah.
based?
Definitely. So but at first, maybe I have to clarify, because there's a point, maybe this was a weakness in that study that we have now also already tackled. What we did is we used the non-dimensional parameters. So instead of having 12 parameters, we only used 3, or in this case 2 parameters as an input to train the model and to get basically 2 output models. But what the problem was that we used non-dimensional inputs to predict dimensional output. And there you have like, this cannot be transformed directly, because we transformed, or basically we predicted the dimensional minimum film thickness instead of the non-dimensional film thickness. So basically this problem, meanwhile, we found out will be resolved to some kind, and you're getting also better results when you employ these methods. Basically, what you have to do is you just have to multiply in basically the radius. Basically, we could do it with the same database we already had. So that's the one point. Still, the non-dimensional groups, they have been established for various, let's say, decades, and have been very widely employed. But still, I believe that one interesting aspect of ANNs can also, or machine learning in general, can be to study the influence of the several or the different parameters, maybe come up with new non-dimensional groups if that's possible, and also to study or tackle exactly that issue of fluid rheology, to see, okay, which parameters actually do we need to predict the film thickness, and which parameters we might omit in the prediction, and also to widen it up. Of course, in our case, we had rheological models in our FEM simulation that are part of the database. If we open it up, because as you said correctly, like there's always this discussion going on about the different approaches, about the different rheological models. In the end, someone will find or formulate a new lubricant that will behave differently, and then like all the prediction accuracy of the models would begin, which of course also holds true for the non-dimensional or the proximity equation. But still, it can maybe be used to find more generalized ways of predicting film thickness with, not taking into account these classical rheological mathematical formulations. But that's one of the aspects we want to tackle in the future as well.
Very, very good. Very, very interesting. Thank you very much. So then I would say we don't have any other questions in the chat or in the group, I think. As that is not the case, I would first of all like to thank all our speakers of today's session. Once again, thank you for taking the time to share with us what you are doing, to talk so openly about your results. And of course, I want to thank my co-organizers, Martina and Michael, of course, for putting in so much work. And then I would say, we hope that in the next year there can be another Tribology seminar series, and we can continue with some interesting topic.
Yes, absolutely. Thank you, everyone. Thank you for giving the time and the space. It was a pleasure to organize this. Also, thanks to Norbert and Michael.
Yeah, thanks Martina, thanks Norbert. Thanks to all the speakers, thanks to all the speakers of all sessions.
Yes,
and
absolutely.
To the YouTube viewers that maybe have not caught the first 2 sessions, they are on our channel. You can find them pretty easily, especially if you already found this video. And they will be updated shortly with correct timestamps, because now the timestamps correspond to the actual CET time.